Welcome dear students, once again we are here to continue with the chapter of relations and functions from where we have stopped in the last video. And in the last video, as I remember, we ended with the definition of inverse of a function. But before going ahead, I'll discuss a question that was asked by someone in the messenger. The question was, how can we differentiate between a relation and a function? So this is a question someone asked me in the messenger, and I'll discuss this question first and then we'll move ahead. To the answer, one thing is clear, that every function is a relation, but every relation is not a function. Converse is not true. To keep it in mind, you can keep FIR. So FIR, you are very much familiar with this term, FIR. So FIR is true, that means every function is relation. But converse is not true. So how to check whether a relation is a function or not? For that, you simply draw the graph of the function. The graph of the function may be of any of these types. The graph may be something like this. 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 This is the graph of some given relation between x and y. Every equation between two variables x and y is a relation. The question is whether it is a function or not. And the test which tells us whether it is a function or not is called vertical line test. So what you have to do, if you can draw a vertical line that cuts the graph in more than 1 points, then it is not a function, it is a relation. For example, in the first one, you can draw a vertical line which cut the graph in 2 different points. So definitely this equation between the x and y is a relation, it is not a function. And what the equation is, it is x square plus y square is equal to k square, and every equation between two variables x and y is a relation. So it is a relation, but it is not a function because you can draw a vertical line cutting the graph in 2 different points. The next one, whatever the vertical line you will draw, the vertical line will cut this graph at exactly 1 point. So the second one is a function. The third one, you can draw a vertical line which cuts the graph in 2 different points. So it is not a function, it is a relation. And what is the equation? Is y square is equal to 4ax, it is a parabola. The fourth one, whatever the vertical line you will draw, it will cut the graph exactly at 1 point. So this equation represents a function, and equation is x square is equal to 4ay, or you can say y is equal to x square upon 4a, or you can say f of x is equal to x square upon 4a. So this is the function which is being represented by this graph. In the fourth case, again, every vertical line cuts the graph in exactly 1 point, so it is again a function, and you are familiar with this graph also. This is the graph of the function fx is equal to mod x. The last one, again, you can find vertical lines which cut the graph exactly at 2 points. So once again, it is a relation, it is not a function. So it is the answer to the question, how to differentiate between a function and a relation. Now we will move ahead. That means from where we have stopped in the last video. In the last video, we have discussed the definition of inverse of a function, that if fx is a function, then another function gx will be its inverse if f composite g is identity function and g composite f is also an identity function. Now the question is how to find inverse of a particular function. Suppose we are given a function fx is equal to 3x minus 1 over x plus 2. Then one thing is clear, that domain of this function is the set of all real numbers other than minus 2, because minus 2 will make the denominator 0, and denominator 0 means the quantity is not well defined. That means minus 2 is not in the domain of this function. Domain is the set of all real numbers other than minus 2. To find inverse, what we have to do, first of all, write y for fx. Write y for fx. What you will get? You will get y is equal to 3x minus 1 upon x plus 2. That means value of y in terms of x. From here, we have to find value of x in terms of y. How to find? Just cross multiply. You will get x, y plus 2y is equal to 3x minus 1. Now, collect all the terms containing x to the left hand side and rest of the terms in the right hand side. So, you will get xy minus 3x is equal to, this will go on the other side, minus 2y minus 1, and now x is common, it is y minus 3 is equal to minus 2y minus 1, or you can say x is equal to 2y plus 1 over 3 minus y. And now write gy for x. As you have written y for fx, now write gy for x. So it will become g of y is equal to 2y plus 1 over 3 minus y. If g of y is this quantity, then what is g of x? Because we normally write a function in the variable x. So I am writing g of x is equal to 2x plus 1 over 3 minus x, and this function g is the inverse of the function f given, and vice versa. Vice versa means f is also inverse of g. So how to find inverse of a function? Another very interesting thing is that the domain of the inverse function becomes the range of the original function. Here, domain of this function is the set of all real numbers other than 3, because 3 will make the denominator 0 and the quantity undefined. So 3 is not in the domain of this function, and this r minus 3, that means the set of all real numbers other than 3, which is domain of the inverse function, is actually the range of the given function fx. So this is the method to find the range of a function as well. So we have obtained the method to find inverse of a function and range of a function. Now one more thing which remains is to verify whether this function is inverse of this function actually is correct or not. So how to verify? Verification is again very easy. We know that composition of a function with its inverse function is always identity function. So that means f composite g should be the identity function, and g composite f should also be the identity function. So let us find f composite g of x, that means g of fx. G of x is 2x plus 1 upon 3 minus x. So what will be g of fx? G of fx will be 2 times fx plus 1 upon 3 minus fx. And now substitute the value of fx. Value of fx is 3x minus 1 upon x plus 2. Substitute it over here. So you will get 2 times 3x minus 1 over x plus 2 plus 1 over 3 minus fx. fx is 3x minus 1 over x plus 2. Simplify. While simplifying, you will get 6x minus 2 plus x plus 2 upon 3x plus 6 minus 3x plus 1. So here 2 will be cancelled, here 3x will be cancelled. You will left with 7x upon 7. 7 will be cancelled, that means x. That means I of x, identity of x. So that means f composite g of x is same as I of x, which means f composite g is identity function. In the same fashion, you can verify that g composite f is also the identity function. So that means whatever the inverse you have obtained is 100% correct, because the composition of the function with the inverse function is coming out to be identity function. So this is how to find inverse of a function. Now we move on to some properties of inverse functions. The properties of inverse functions as well as the properties of composition of two functions. First property is that if f, g are both 1, 1, then their composition function f composite g is also 1. So how to prove it? The proof is very easy. You start with f composite g of x is equal to f composite g of y, and what we have to prove that x is equal to y. If f composite g of x is equal to f composite g of y implies that x is equal to y, then the function f composite g will become 1. So f composite g of x, that means g of fx is equal to g of fy. That means image of fx and fy under the function g, they are same, but the function g is 1, 1 we are given. If 2 points are having same image under some 1, 1 functions, that means the 2 points must be same. So if g of fx is equal to g of fy, then it means fx must be equal to fy. Why? Because g is 1, 1. Now in the same fashion, fx is coming out to be fy, but the function f is also 1, 1. So fx is equal to fy and the function f is 1, 1 implies that x is equal to y. It is because f is 1, 1. You have started with f composite g of x is equal to f composite g of y, and now you arrived at x is equal to y. That means if the image of 2 points under the function f composite g is same, then the points are also same, and it proves that the function is 1, 1. So this means your function f composite g is a 1, 1 function. So it is proof of the property that if two functions are 1, 1, then their composition function is also 1, 1. The second property is very much similar, that if two functions f and g are both onto, then their composite function f composite g is also onto. And the proof is once again very easy. What we have to prove that actually f is function from x to y and g is function, because g will be implied, we are talking about f composite g. So g of fx. G of fx means range of f will become domain of g. So range of f is y. So what will be the function g? G will be from y to z. And what will be the function f composite g? F composite g will be the function having domain of f and range of g. So domain of f will be x and range of z, g will be z. What we have to find we have to find for every z in z there exists some x in x such that f composite g of x is equal to z. That is what we are to establish to make this function onto. So we start with for every z belonging to z. We start with this for every z belonging to z. Now look at this function. Look at this function g. G from y to z is onto. So for every z belonging to this z, there must be some y here such that g of y is equal to z because g is onto. So there exists some y in y such that g of y is equal to z. It is because g is onto function. This is the reason for what? Now, this y and for every y belonging to y, for this y I am talking about now, for every y belonging to y, now concentrate at this function. This function f from x to y is also onto. So for every y here in this y, there must be some x here such that f of x is equal to y because every element here must have some pre-image. So for every y in y, there exists x belonging to x such that f of x is equal to y. And put this value of fx is equal to y here. So what you are going to get, for every z in z, there exists x in x such that this g of y, but y is equal to fx, so g of fx is equal to z. That means f composite g of x is equal to z, and that is what we want to establish. We wanted to establish the same thing, and this proves it proves that the function f composite g is onto. So if f and g are onto functions, then their composition function is also an onto function. So from these two results, we can deduce that if f and g are both invertible functions, that means bijective, then their composition function f composite g is also a bijective function, that means invertible. Why? Because f and g are bijective means f and g are 1 1 and f and g are onto. F and g are 1 1. From here we will get f and g, f composite g is 1 1. F and g are onto. From here we can deduce that f composite g is onto. So f composite g is 1 1 as well as onto, and a function which is 1 1 as well as onto is a bijective function. So f composition with g will also be a bijective function. Now, there are some questions. How many 1 1 functions will be there from a set x to a set y? How many normal functions, simple functions will be there? How many onto functions will be there? So this point I'll be discussing now. So suppose you are having two sets, A and B. Number of elements in A, B, m, and number of elements in B, B, n. Suppose this is the case. Now, how many functions will be there from A to B? This is your A, this is your B. Here you are having elements A1, A2, A3 and so on, Am. Here you are having elements B1, B2, B3 and so on, Bn. To define a function, how many possibilities are there for the image of A1? Because every element must have a unique image. So A1 can have an image in how many ways? In n ways. So this element can have image in n ways. It can have any image. It can have B1, it can have B2, it can have B3, it can have Bn, any image. Similarly, how many possibilities are there for the image of the point A2? So A2 can also have images in the same n ways. A2 can have image B1, A2 can have image B2, A2 can have image Bn. So once again there are n possibilities. Similarly, for A3 there are n possibilities, and so on. For Am there are n possibilities. So total number of possibilities is n multiplied by n multiplied by n multiplied by n, and how many times? It is m times, because it is for A1, for A2, for A3, for Am. So these are m n's. So n multiplied by n multiplied by n m times will become n raised to the power m. That means from a set A to the set B, how many functions can be there? The number of functions can be n raised to the power m. So this is answer to our first question, how many functions are there from a set A to the set B. Now we move on to the second part, how many 1-1 functions are there from the set A to the set B. I am rewriting here A1, A2. Now, how many possibilities are there for the images of the point A1? So A1 can have any of these images. So it can have n images. The number of possibilities is n. Suppose A1 goes to some point here BI. Now we are considering the case of 1-1 functions. So every 2 points will have different image now. If A1 occupied BI, then no other element A2, A3 or AN can be associated with the same BI. So this is ruled out now. For the next image, for A2, how many possibilities are there? This is not a possibility now, keep it in mind. Total number of elements is n, but this one is not possible. So how many possibilities are there? The number of possibilities is now n minus 1. This is for the second element. Now suppose A2 goes to some element Bj. So this possibility is again crossed, because now next element can neither go to Bi nor go to Bj. So for A3, now the number of possibilities is n minus 2. And so on. For the last, for first element, it is, you can say n minus 0. For first element, n minus 0. For second, n minus 1. For third, n minus 2. So for mth element, the number of possibilities will be n minus m minus 1. So what is the total number of possibilities is their product. But it is not easy to keep it in mind, to remember this product in this form. So what we do, we will write it as n minus 1, n minus 2 and so on, n minus m minus 1. And now I multiply and divide this quantity by n minus m factorial. I multiplied it by n minus m factorial. So here it should be n minus. So it will become now, in the numerator, it will become n factorial divided by n minus m factorial. Multiply it by m factorial and divide by m factorial. So what this will be, this will become NCM. So it is NCM multiplied by m factorial. This is the total number of 1-1 functions from the set A to the set B. But there is one thing to be remember, that this is possible if and only if m is less than or equal to n. Because if m is greater than n, then 1-1 function will not be possible, because the number of images is less and the number of elements in A will be more. So this is the second case, the number of 1-1 functions from a set A to the set B. And now the third one is that how many functions will be there from A to B, which are on to. I'm just going to write the formula. I'll not be going into details. It will be m raised to the power n minus m plus m minus 1 plus m minus 1 raised to the power n plus mc2 m minus 2 raised to the power n and so on, minus and so on. This will be the formula for number of onto functions from the set A to the set B if m and n are the number of elements in the sets A and B. Someone may ask, what will happen if A or B or both are fine? It may be a question. So if A is fine, B is not fine, whether it will be a function or not? Yes, it will be a function and will be called empty function. What will happen if A is not fine and B is fine? The function is not possible. Function is not possible. What will happen if A is fine and B is also fine? Then the function will be called void function. Void function. So it may be a question in mind whether there will be a function if A or B or both A and B are fine. So one more thing to be kept in mind. What will happen if the function f from a set A to the set B is 1, 1 and onto? If there exists f from A to B which is 1, 1 and onto, then cardinality of A will be same as cardinality of B. Cardinality means the number of elements. So if there exists a function A to B which is 1, 1 as well as onto, then number of elements in A and number of elements in B will be same. A very interesting question now for you. There are two sets N and Z. N is the set of natural numbers, Z is the set of integers. If I ask you which of these two sets have more elements and which has less number of elements, your quick answer will be number of elements in the set of natural numbers is less than number of elements in the set of integers. But answer is not correct. Reason being, I can have a function from the set N to the set Z which is 1, 1 as well as onto. And you know, if there exists a function from N to Z which is 1, 1 as well as onto, then cardinality of N and cardinality of Z are same. That means number of elements in the set N and the number of elements in the set Z are same, equal. So the next question is what that function is. So the function is very simple. I am going to define f from N to Z defined by f of N is equal to n by 2 if N is even and minus of n minus 1 by 2 if N is odd. Now look at this function. What is going to happen here? This is your set N and I'm having this is set and Z. Members of N are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on. On the other side, members of Z are, I'm starting from 0 here, 1, 2, 3, 4, 5, 6 and so on, minus 1, minus 2, minus 3, minus 4, minus 5 and so on both sides. What is the image of 1? So f of 1, here 1 is odd. So if 1 is odd, image will be minus 1 minus 1 by 2. 1 minus 1 is 0, so image of 1 will be 0. Image of 1 is going to be 0. What is image of 2? 2 is even. So its image will be 2 by 2, that means 1. So image of 2 is 1. What will be image of 3? 3 is odd. So image will be minus 3 minus 1 by 2. 3 minus 1 is 2, 2 by 2 is 1, and there is a negative sign here, so it is minus 1. Image of 3 is minus 1. Similarly, image of 4 is 2, image of 5 is minus 2, image of 6 is 3, image of 7 is minus 3, image of 8 is 4, image of 9 is minus 4, image of 10 is 5, and so on. Look at every two distinct elements are having different images in the set Z. That means the function is 1, 1. Secondly, start from 0, go in increasing order or go in decreasing order. Every element is having some pre-image. That means the function is onto. This function is 1, 1 as well as onto, which makes the cardinality of two sets equal. That means number of elements in the set of natural numbers is exactly same as the number of elements in the set Z. Another very interesting question. If I ask you, I am having two intervals. One is the open interval 0, 1 and another is the open interval 0 to 100. That means the set of all real numbers between 0 and 1 and the set of all real numbers between 0 and 100. If I ask you which of these two sets have more number of elements, once again your quick answer will be the second one, that is the open interval 0, 1. But once again the answer is not correct, because once again they are having the same cardinality. Why? Once again, if they are having the same cardinality, then there must be some function from this interval to this interval, which is 1, 1 as well as onto. So in general, I am not taking these two intervals. I take in general two intervals AB and CD. Now, you can take A as 0, B as 1, C as 0, D as 100. You can take any values. That means for any two open intervals, I am going to prove that they are having same cardinality. And for that, I will have to define a function from this interval to this interval, which is 1, 1 as well as onto. So the function is f from AB to CD, defined as f of x is equal to c plus d minus c upon b minus a times x minus a. This is the function, and I leave it for you as an exercise to prove that this function is 1, 1 as well as onto. And if someone will ask me in the comment box to prove that this function is 1, 1 and onto, definitely and surely in the next video I will prove that this function is 1, 1 as well as onto. Now we have defined a function from the interval AB to the interval CD, which is 1, 1 as well as onto, which proves that the cardinality of these two intervals is same. Now whatever the values of A, B, C, D you will put, these two intervals will have same number of elements. So that means the open interval 0, 1 and the open interval 0, 100, they are having same cardinality, means the same number of elements. So here where I am going to end this chapter, relations and functions. In the next video we will meet with the next topic. But before ending this video, I must thank you for liking my videos, for sharing it with your friends, with students especially of class 1, and I must thank you for subscribing my channel at large. Thanks, and thanks dear students.